Hello everyone, my name is Ali and I will present to you the second part of our set of lectures, which is Introduction to Adaptive First Order Methods. Basically, in this lecture, I will introduce you to adaptive methods, what they are, what are their main properties, and what are different variants of adaptive methods, and how they are different than gradient descent or stochastic gradient descent. And while explaining those, I'll try to take a particular perspective to the notion of adaptivity. And in the next lecture, we're going to see another notion of adaptivity. So let's start. For the rest of the lecture, I will consider this simple optimization problem, which is minimization of some function f, subject to some constraint. Here, our function f could be convex, non-convex, smooth, or non-smooth. And depending on the setting, we may assume certain properties for the set x here. When x is a whole space, this is basically the gradient descent scheme that we have. This is a general scheme that we have. So one thing that I would like to mention is, in this lecture, the small t refers to the current iteration, and the capital T refers to the time horizon until which we run our algorithms. And from time to time, we may require the knowledge of this t to show some better convergence properties. So in this template, gt is our gradient, which is our negative descent direction. And we have a step size eta t. It can be a constant, it can be something time dependent, it can be dynamic. And what happens is from xt, we are taking a step in the negative gradient direction, and we are arriving at our next point. If we consider gradient descent, for smooth functions, gt is the gradient of the function. And when the function is not smooth, it's a subgradient of the function at point xt. So when we're dealing with stochastic gradient descent, SGD, the assumption we have is our estimates GT are unbiased, meaning in expectation, they are either equal to the gradient of the function for the smooth setting, or they are some subgradient in expectation. And also, with respect to the convexity of our objective function f, we need to define different notions of convergence. So when f is convex, we will be interested in the value convergence, meaning how fast f of xt converges to the optimal value f of x star. And if you're dealing with stochastic gradients, we will be interested in the expected value of this difference. And for non-convex, our focus will be first order stationarity, meaning we're interested in how fast the gradient, norm of the gradient, converges to zero. Given those, let me talk about some standard rates for gradient descent and SGD for convex functions. Let's start with gradient descent. If our function is L-smooth, meaning its gradient is L-Lifshitz continuous, we can select a fixed step size, which is less than 1 over L. And in that case, we can guarantee a convergence of 1 over T. But when our function is non-smooth, or when our gradients are stochastic, what we have is we need to have a decreasing step size, such that we need to decrease our step size at a rate of 1 over square root of T. And in that case, our rate deteriorates slightly and becomes log T over square root of T. The reason for SGD, why we have a decreasing step size, is that since we're dealing with gradient estimates rather than the true values, we need to control the noise in our gradients because there is a variation in the estimates from the true value. And in order to control the effect of the noise, we need to decrease our step size to guarantee the convergence. One thing that we can do to improve the results that we have is, if you know the time horizon capital T, instead of having a time-dependent decreasing step size, we can choose a fixed step size, which is 1 over square root of capital T. And in that setting, we can get rid of the log T factor and then have the convergence of 1 over square root of capital T. What I would like to talk about is two observations about gradient descent and stochastic gradient descent. Actually, the way we select our step size. So if you look at the smooth setting with gradient descent, we select a step size, which is constant, but it depends on the global information L, which is the worst case constant that we can have to satisfy the smoothness property in the whole space, or the space that we define our function in. And when we look at SGD, we have a decreasing step size, and this strategy is fixed irrespective of what kind of a function we have, or the particular local information, the gradient information we have, the objective value, if we can access it, we have. It's just a fixed strategy which we determined even before the execution. So the question is, if we can exploit the local information, like the gradients themselves or the objective value at the points, can we customize our step size to achieve something better in certain cases, or at least achieve the same convergence rates that we have in this table? So the answer is yes, and we will see a general template for such methods. So in this template, we will start with the gradient descent scheme. We have a gradient estimate GT. We take the gradient step, we project it onto the set X, and then we compute our next iterate. So this PX stands for projection, orthogonal projection onto the set X. And this is written in this way. This is the Euclidean norm. There's nothing complicated or special about this. So adaptive methods can actually deal with the gradient estimates and also the step sizes in the following way. So we introduce MT, which we call the first order estimate. And what happens is, instead of using the last gradient only, we can use some combination of the history of gradients that we have, so that we're computing a new negative descent direction. Instead of using the last estimate or the last gradient, we can use some combination of the history. And if you look at it, SGD and GD, they're actually using MT equals to GT. They're not considering any previous gradient information while deciding on the descent direction. And the second thing that we can do is, instead of having a scalar step size, which is predetermined, we can compute it dynamically in the following way. So this HD is again a function of old history of gradients. And we call this a second order estimate because we are taking the outer product and we are accumulating those outer products in a certain way. Most of the time, and actually in the rest of this in this lecture, we will see adaptive methods that actually use the diagonal of HD only, meaning instead of accumulating this whole matrices, they're taking the element y square of each estimate and then summing them up in some particular way. So this eventually leads to having a per coordinate step size, which is computed dynamically based on the gradient information. And for gradient descent and SGD, this HD function is basically identity because we are not dealing with any dynamic selection. And when we introduce the second order estimate, we change our projection to metric projection. So if this H is identity, this is basically the Euclidean norm, and this becomes the orthogonal projection. But here we have an H which is positive definite. And since I am going to assume that this is going to be a diagonal matrix for simplicity, it means we're putting different weights across different coordinates while computing this projection. So let's move on and see our first adaptive algorithm. We'll start with AdaGrad, which is the pioneering work that actually gave rise to the other methods that we're going to see today. It was proposed by Ducci and co-authors. What AdaGrad does is it doesn't have an estimate for GT. It uses GT itself. But what it does is it accumulates the outer products, it sums them up, and then it takes a diagonal, as I mentioned previously, and it takes a square root and then computes the inverse of this matrix, which is easy, which is basically inverting every element in the diagonal. And then we have a per coordinate step size. And if you multiply the inverse of this HD with GT, it means we have a per coordinate step size. A simpler version is the AdaGrad scalar, in which we are accumulating the norms of the gradients rather than the outer products. So we have a scalar here. We take the square root, and then we divide our steps, our initial step size eta with square root of qt. So to put things in a simpler manner, this is how we accumulate the gradients. We accumulate gradient norms such that now we have a decreasing, or let's say non-increasing step size. And other grad is basically the same, but this idea applied to every coordinate, meaning for coordinate I, we are accumulating ith coordinates of all the gradients. We take the square of those elements, we sum them up and take the square root, and then apply the same descent for every coordinate separately. So the question is, how is this going to help? Or what is the intuition behind this notion of adaptivity? So to do so, I'll first give you a high-level idea, and then we will move on to simple proof. We're going to jump to a certain step of the proof of other grad, and we're going to see how we should actually understand this from a theoretical perspective. Let's start with this same optimization problem. We're going to make certain assumptions on this at the moment. I will assume that the f we have is non-smooth and it's convex. Since we don't need smoothness here, we can assume that it's just non-smooth. Our set, the constraint x is again convex, and it's compact, meaning it's closed and bounded, so that our iterates are eventually bounded since we're using a projected update. And we're going to define a quantity d, which is what we call the diameter of x. Specifically, it is a maximum distance between any 2 points that is an element of the set x. So for the sequel, I will focus on other grad scalar because I believe it's going to be an easier choice, but we can also show the same results for the other grad, the original other grad itself. So we have this decreasing step size, and the idea is the following. So if we observe gradients with large magnitude, then our step size here will decrease faster. And the intuition could be, if our step size is too large, with very large gradients, then our iterates may diverge, or it will oscillate in some manner around the minimum, but does not converge because our step sizes are too large. So other grad tames the step size in the presence of large gradients. And the opposite is also true. If we have small gradients and our step size does not become very small, it kind of stabilizes, so that with small gradients, we can still make progress without decreasing our step size any further. And let's assume that our gradients have more or less similar gradient norms, or more or less similar magnitudes. In that setting, the step size grows as 1 over square root of d, which is similar to what SGD does. And hence, we are selecting our step size adaptively depending on the magnitude of our gradients, that the history of the magnitude of the gradients that we observe. Okay, so let's move on to the theoretical proof. I mean, this is not a full proof. This is just a few steps of the proof, which I believe is the most relevant for explaining the other grad step size. And in this setting, we won't make any structural assumption about eta t. We just assume we don't know how to apply the grad. And the goal here is that we want to show value convergence with respect to x bar t, x bar capital T. And this x bar capital T is the uniform average of all the iterates that we've seen so far. And our only assumption about the growth of eta t is it is non-increasing. It can be constant, it can be decreasing, or it can be a combination of both, but we don't want it to increase because this is something that we exploit in the analysis itself. Okay, so let me basically jump to the very end of the analysis. Okay, so this quantity, this objective difference, is upper bounded by 1 over t times this value, this expression. So in this expression, I think we can get an idea about how we are selecting our step size, other grad step size from this term. But the problem is, if we select this too small, then this term becomes very big. If eta t capital T is very large, since it's non-increasing, then this will be, this is going to be very small, but this term is going to be very large. So essentially, we need to find a middle ground. And for that, I propose, let's use the intuition that we got in the beginning, such that let's assume we have a constant step size and that we know the time horizon. So if we set this eta t and eta capital T as eta, a fixed step size, what happens is we have a linear function of eta plus 1 over eta. And this summation actually has a minimizer, which we can attain. This is basically a convex function that we can optimize to find the best bound and the corresponding step size. And if we do so, we take the derivative, we equate it to 0 and find the eta that gives the optimal value. What we find is the step size. And if you plug the step size into this expression, we're going to obtain the following convergence rate. Okay, the problem here is our step size is not very realistic, right? Because we're assuming, even in the first iteration, we should know all the gradients that we're going to see to compute our gradient. But this is, of course, not realistic. It's not achievable. So we need to talk about what is the second best thing that we can do. And I think it's kind of obvious that instead of summing everything up to the time horizon that we don't know, we can compute the following step size, which is something d over square root of sum of all the gradient norms until this point. And this two factor is necessary to optimize the bound. But we can ignore it. The important thing is we need to sum things up to the current iteration. And if you take this decreasing step size, basically because these are positive values and it decreases or non-increasing, if you plug this in using some technical lemmas, we can obtain this following convergence rate. So for the full proof of it in the setting of original undergrad, I would like to point out to you to the original paper. It's the analysis is pretty standard and it's pretty clearly written, so you would understand how we actually end up at this stage. And the good thing is we actually proved how we actually obtained the undergrad step size in the first place, and we've also shown the adaptive convergence bound for undergrad. So as we said previously, our rate in the most optimal setting was this, and now you're just suffering a square root of t factor, which is, I think, acceptable. And the good thing is, we also see that not only our step size is adaptive, but our convergence rate is also adaptive, and it depends on the local information. It depends on our observed gradients. So assume that our gradients were very, very small, or they become very small very fast. So then we have a better convergence rate. And if we have very large gradients with very large magnitudes, then our convergence rate could be a bit worse than the first case. To formalize everything and to give you the relevant convergence rates in the literature, let's first start with the original result. So I'm gonna assume that our function is G Lipschitz. It's non-smooth, but its gradients have an upper bound. The norm of the gradients of f are upper bounded by G, the subgradients. And our function f is convex, and that's our x is a compact set so that we can define its diameter d. And if we select the step size as I just shown, this is the adaptive bound we get. And using the G Lipschitzness of the function, we can get 1 over square root of t rate. I can also say that instead of using deterministic gradients, if we use the stochastic gradients, with an additional assumption that in expectation, norms of gradients are bounded by G, again, then we can actually obtain the same rate. And we have a more recent result for the smooth and stochastic setting. So in the setting, we're going to assume f to be L smooth convex, and that the global minimizer of f lies in this compact set X. Instead of using this expected gradient norm boundedness, we're going to assume bounded variance for the gradients, meaning in expectation, our gradient estimates cannot deviate too much from the true gradient. But I would like to note that this bounded variance assumption does not say that our stochastic gradients themselves are bounded. It's just assume the Gaussian distribution. The random variable is not bounded, but its variance is bounded. So this is the same setting. It's just that in expectation, it shouldn't deviate too much from the true value. And in this setting, we can again show the 1/square root of the convergence rate. So what is interesting about this, and this is actually the topic of the next lecture, but if we consider the setting where sigma is actually 0, meaning we're in the deterministic setting, then Alacaoglu achieves the same rate as gradient descent. So this is another notion of adaptivity. And we're going to see this notion in the next lecture. But I think the important thing is, in this, we're actually painting the whole picture here. In the non-smooth setting, we have the 1/square root of t rate. When smooth stochastic, we have 1/square root of t. When it's deterministic and smooth, we have 1/t. So Alacaoglu is basically achieving the same rates as GT and SGD achieve. And one last thing is, I would like to talk about its behavior in the non-convex. So we won't be making the assumption of bounded domain in this setting. And we are, again, focusing on Alacaoglu scalar. And by the way, this result is concerned for Alacaoglu scalar, but I believe similar results may be shown for Alacaoglu itself. So again, here we have Alacaoglu scalar, and our function is now non-convex, it's smooth, and our gradient estimates are stochastic. And the one thing to notice is that now our notion of convergence changed. Now we're interested in how the gradient norm evolves. And one thing also to pay attention to is, although we never observe full gradients in this algorithm because it's the stochastic setting, we are giving the rates with respect to the full gradients. And this is something standard, something that you would see in the literature. And with respect to the minimum of such gradients, evaluated at the history of interest that we have, we can show a convergence of 1/square root of t. Another thing that I'd like to mention is, we're showing here the convergence not in minimum of expected norm of the gradients, but with probability. So this is another notion of convergence, which we haven't discussed, but since I believe this would introduce us to a new notion, I would like to include this one. So basically, with high probability, meaning as we take delta to 0, this becomes a high probability result. But the problem is, as we decrease delta, we are actually making this convergence rate worse. But this is actually one notion of convergence that you would see for non-convex problems. Rather than in expectation, with some probability, you would have a convergence rate like this. Okay, from this point on, we will move on to the variants of Alacaoglu. And the first variant that we're going to see today is called RMS prop. So to recall Alacaoglu, we weren't accumulating any previous gradient information. We were just dealing with the latest gradient, but we were accumulating linearly these outer products. We were summing them up. But what RMS prop does is it computes a convex combination of the previous estimate, previous second order estimate, and the current outer product. And this convex combination actually leads to something that we call the moving average, meaning the latest gradients have relatively higher weights than the previous information. And as we move forward in our execution, early gradients, early outer products have their weights decreasing, while the latest gradients have the largest weights. So this difference, we will talk about this, but let's put them in a simpler form. Again, we know this is what Alacaoglu does in every coordinate, and this is what RMS prop does in every coordinate. And we can see that as we are moving forward with our iterations t, then every gradient information suffers an additional beta as t increases. So we are multiplying this with beta with every new iteration. So as I said, the intuition is the recent gradients receive larger weights, and as we move forward, earlier gradient information actually have its weight decreasing. So how is this important, or in what settings does this actually make sense? So let's assume a very flat function around its minimum, like x to the 4. It's very flat around the minimum, but it increases very fast as you move away from the minimum. And what happens is, let's assume that other graph starts from this very steep region. It accumulates very large gradients, its step size decreases so fast, and when it reaches the flat region, it observes very small gradients and it has a very small step size. But our MS probe can actually recover from this. Because, okay, as RMS probe sees smaller and smaller gradients, those smaller gradients will have larger weights rather than the history, rather than the early iterations in which we saw very large gradients. They're going to lose their weight, their weights are going to decrease, and the gradients with smaller weights are going to have higher. Gradients with smaller magnitude are going to have higher weight, so that this QT will actually decrease and the step size will increase. So to demonstrate that, I actually have a very simple set of plots here. So this is just a one-dimensional example. We have x to the 4. Of course, we know its optimal value, but this is just to show the behavior in practice, in action. So we have x to the 4, and both algorithms start from value 10, and we know the optimal value is 0. What happens is, AdaGrad decreases its step size here very fast, and then it never recovers. Since it keeps seeing large gradients, it's going to accumulate them, and its step size decreases. But RMS probe, what it does is it actually recovers. It can actually increase the step size if the newly observed gradients have relatively small magnitudes than the previous ones. So this may eventually lead to a better convergence for RMS probe. So these figures are not telling us that RMS probe is better than AdaGrad, but there are certain cases in which RMS probe-like methods, which uses a moving average for the second order estimates, could actually benefit and exploit the local structure, or at least the local and global structure better to have a better convergence rate. So on top of this RMS probe, it was proposed by Geoffrey Hinton in one of his lecture notes. And RMS probe is just a small modification over AdaGrad. But we can actually make another modification on top of RMSGrad as well, which becomes the Adam algorithm. I would say Adam is probably the most famous among all these adaptive algorithms. So the core difference between RMS probe and Adam is it has the same moving average for the second order estimate, but what changes is it does the same moving average trick or moving average scheduling for the first order estimate here. And the rest is the same. And we have this epsilon value. This is actually, you would add this to all other methods, to RMS probe, to AdaGrad as well. This is for numerical consistency. And for Adam, as you can see in the footnote, we have a bias correction step, such that every iteration we are dividing MT and QT to some value, and this is basically to deal with the bias of these estimates. But I'm going to ignore these because they are not directly relevant to our purposes. We're interested in why these structures make sense in the way they are constructed. So to be honest, it's not as easy to explain the difference between RMS probe and Adam than the difference between AdaGrad and RMS probe. But I could tell you the following. So let's assume the same setting, that we have the x to the 4, which is flattened around the minimum. And as you move away, the function increases with increasing gradients. So what happens is both of RMS probe and Adam started from the steep region. They arrived at the flat region. The main difference between RMS probe and Adam when they arrive at the flat one is RMS probe needs to still deal with small gradients. But since Adam is averaging these gradients in a moving in this moving fashion, the gradients which have larger magnitudes would still have an effect on this first order estimate. So essentially, Adam would have a pretty much similar second order estimation, but its first order estimates would have a large magnitude, so it may contribute in its convergence in this flat region. Again, this is just a very, very rough intuition, but I think this is one way of interpreting it. Unfortunately, theoretically, although practically Adam is usually the choice among all these algorithms, the problem is, theoretically, Reddy and co-authors, they discovered the problem in its convergence. Specifically, if we consider that we have constant beta 1 and beta 2 for Adam, meaning these averaging parameters for first and second order estimates. What happens is, if they satisfy this, meaning beta 1 is smaller than square root of beta 2, then there exists a stochastic convex optimization problem for which Adam does not converge to the optimal value of the problem. And they're showing a counterexample in their paper, and they're showing that how you can actually remedy this problem, which is the algorithm here, AMS-grad. But the reason why this is happening is, again, this property, the same property that RMS-prop has. This quantity is not monotonic. As we've seen in this plot, the second order moment across any coordinate actually can increase. So theoretically, this creates a kind of a problem. So people solve this in different ways, but AMS-grad solves this in the following way. So instead of having QT as is, they are dealing with the maximum of QTs across all the iterations. So this that basically computes the maximum QT so far for all the coordinates, and then it applies the same update rule with respect to this Q hat T. And what this eventually leads to is that we have a monotonic quantity for the second order estimate. And for AMS-grad, the authors prove some rates, and later a more recent work prove rates in other settings. So our set of assumptions for AMS-grad and its theoretical convergence properties are the following. So we're going to assume that gradients have a bounded L-infinity norm. So if you assume that our function is G-Lipschitz, then this is kind of like a natural corollary of this. And we also assume that X, our compact set X, has a diameter in L-infinity norm as well. And the original paper claims that for non-smooth F and for convex F, we have a compact function set X over which we are optimizing our function F. Then if we choose our eta t here, just go back here, as a decreasing function, which decreases as 1 over square root of t, then one can show that AMS-grad convergence at the rate of log t over square root of t. And as I said, if you make the assumption that the gradient norms are also in expectation bounded for stochastic functions, you can also show the similar rate for the stochastic setting. And this is, again, compatible with what we've seen for SGD with a decreasing step size. But we can also show convergence rates for the non-convex setting. So we have a very recent result, which deals with AMS-grad. So again, we are in the non-convex setting. Our function is smooth. And we again assume that, okay, there's a typo here, that the gradients have a bounded L-infinity norm. Again, with a decreasing step size of this form, we show that minimum of the expected norm of the full gradient decreases as log t over square root of t. So here we're showing the convergence with respect to the expected norm rather than the high probability result that we've seen in other grad. And this I decided to keep because this is the original expression that happens in the paper. But what you can do is you can take the minimum of these sequence and then take it out, and you basically have this rate. And another relevant result is that if you have a fixed step size in which you assume you know the time horizon, and of course some other parameters that I ignored here for convenience, you can show the same convergence rate with 1 over square root of t without the log t. And these are the natural results. And if you're interested in, you could go ahead and read the papers for which I have the references at the end. So this is basically the end of our lecture for the theoretical part, but I'll conclude with a plot over which I try to show the performance of SGD and all the adaptive methods that we've seen today. So we have a least squares problem here, which is a convex problem, and we're dealing with synthetic data. So here, this is the least squares formulation, and the way we generated the matrix A is that every element of A is coming from a distribution, which is a Gaussian with mean mu and variance sigma squared. So after generating A, how we generated B is we picked an optimal value X randomly, we multiplied it with this A, and then we had a little bit of perturbation and then obtained B here. So A is here a square matrix, and all of the methods here, they start from the same random point. And the way we compute their stochastic gradients is we select 20 data points from the matrix A, randomly selected every iteration, and we compute our mini-batch stochastic gradient estimates using these random data points. And I think what we need to take away from this plot is the following. So SGD in the beginning seems to do a better job, and it outperforms most of the methods, I mean, all of the methods until a certain point. And after this point, in this regime, SGD shows a rate of almost 1 over square root of t as expected. But we see that, especially at the AMS grad and other grad, they're actually showing a convergence rate which is better than 1 over square root of t. And RMS probe starts off slow, but then it catches up with AMS grad. And Adam, which seems to converge earlier than we expect, but I didn't run this any further. Maybe it's also continue to decrease, but the reason for this behavior is related to tuning the initial step size as much as beta 1 and beta 2. And I did a rough tuning for all of the methods to be fair to all. So this is just a tuning issue which should be fixable. And if you look at the step sizes, so for SGD, what you see here is the initial step size of SGD. And the interesting thing is they are all starting from the same point, more or less, in terms of their step size. AMS grad and other grads, they're monotonic and they converge to a certain value. But what happens with RMS probe and Adam here is that, so in this region, they probably observe gradients with decreasing magnitudes. And then their step size starts to increase. And then in that region, in which we see that their step size seem to stabilize, what they observe is probably gradients with more or less equal magnitudes, so that their estimate has a magnitude which doesn't change much, which converges to a certain value. And this happens when they get close to the optimal value. As I said, the take-home message from these plots is adaptive methods and for certain problems may adapt to geometry better such that they show improved rates than the standard methods such as SGD. To wrap up, we started with gradient descent and SGD and their convergence properties for convex problems, their rates and their corresponding step sizes. Then we moved on to a general template of adaptive methods with first order and second order moment estimation. Then we've seen our first adaptive method, which is other grads. We gave a little bit of intuition to it with the proof of its step size selection, and then we gave its convergence rates for convex and non-convex problems. Then we moved on to RMS probe, which is other grad with moving averages of the second moments. We compared it to other grad and argued about in what case RMS probe could be better than other grad. And then we've seen Adam, which I would say a generalization of RMS probe, with an addition of first order estimation using the smoothing average idea. And finally, we have RMS grad, which theoretically solves the problem of a non-convergence of Adam. And then we proposed its convergence rates for convex and non-convex problems. So this basically concludes this lecture. Here are the references that were included in this lecture. Thank you for listening.